Hello everyone and welcome back to Math Made Easy. In the previous two lectures, we studied two important direct methods for solving systems of linear equations. First, we learned the Gauss elimination method where we transformed the coefficient matrix into an upper triangular matrix and then applied back substitution to obtain the solution. And after that, we started the Gauss-Jordan elimination method, where we continued the elimination process until the coefficient matrix becomes the identity matrix and allowing us to read the solution directly. And both the methods are efficient when solving a single system of equations. However, let's just consider a very practical situation. Suppose an engineer needs to solve this ax equals to b1, then ax equals to b2, and then ax equals to b3. Now notice something interesting here, that this A is the coefficient matrix that remains exactly the same, only the right hand side changes here. So if we use Gaussian elimination every time we repeat the same elimination process again and again, and this is inefficient. Wouldn't it be better if we perform the elimination only once, stored the result, and then reused it whenever required or whenever needed? So the answer is LU decomposition. So instead of repeatedly reducing the matrix, we decompose it into two simpler matrices as a lower triangular matrix and an upper triangular matrix. Once this decomposition is obtained, solving multiple systems becomes much faster. And this idea is widely used in engineering software, scientific computing, or even in machine learning, scientific or numerical simulations. So today we'll understand how this LU decomposition works and how it is all derived and how it is used to solve the system of linear equations. So let's just understand the need for LU decomposition through a very practical example. So suppose we have this matrix that A is equals to this 2, 1, minus 1, minus 3, minus 1, 2, minus 2, 1, 2. Now suppose we need to solve this ax equals to b1 today and this ax equals to b2 tomorrow and ax equals to b3 next week. Should we perform the Gaussian elimination every time? No. Instead, we perform elimination only once. The elimination information is stored in two matrices here, that is this L and U. And then solving any new system requires only substitution, making the computation significantly faster. This is the central idea behind this LU decomposition. Now, before learning this LU decomposition, we must understand the two special matrices here. That is the lower triangular matrix, a matrix in which all the entries above the main diagonal are 0. And now notice 0. That is this L equals to this 1, 0, 0, L2, 1, 1, 0, L3, 1, L3, 2, and 1. Notice that every element above the diagonal is 0 here. The diagonal entries are usually taken as 1 in Doolittle's method, which we will study today. And this upper triangular matrix U will be just U11, U12, U13, 0, U22, U23, 0, 0, U33. Here every element below that main diagonal is 0. And the objective of this LU decomposition is A is equals to LU, where this L is lower triangular and U is upper triangular. Now let's just understand the mathematical idea behind this. So suppose we have this AX equals to B, and if A is equals to LU, then we can substitute it here and obtain this LUX equals to B. Now introducing a new variable, that is this ux equals to y, therefore the original problem becomes ly equals to b. And after solving, we get this ly equals to b and ux equals to y. Now notice something important. Both the equations involve the triangular matrices, and the triangular systems are very easy to solve. The first uses the forward substitution. The second uses the back substitution. Thus, instead of solving one complicated system, we solve two much simpler systems. And this is the beauty of LU decomposition. Basically, there are several methods of obtaining this LU decomposition, but the most common are this Doolittle method, this Crout method, and this Cholesky decomposition. So, in today's lecture, we'll study this Doolittle method. Its defining characteristic is taking this diagonal elements of LR equals to 1, as is L and U. Now let's just learn how to obtain the matrices L and U here. We have this A is equals to this 2, 1, minus 1, 4, 5, minus 3, minus 2, 5, and minus 2. We are assuming that this A is equals to LU, then letting this L and U as this and multiplying these two matrices together, so we get this LU as U11, U12, U13, L21, U1, L21, U12 plus U22, this L21, U13 plus U23, this L31, U11, L31, U12 plus L32, U22, this L31, U13 plus L32, U23 plus U33. And since this A is equals to LU, the corresponding elements must be equal. So this is the key idea of LU decomposition. We compare corresponding entries of the matrices to determine the unknown elements of L and U. Rather than memorizing the formulas, let's just understand the order in which we compute the entries. Basically, to define the Doolittle algorithm. So first we need to compute this first row of U, then first column of L, and then second row of U, and then second column of L, and continue until all the unknown entries are obtained. And once this L and U are known, solving the system becomes straightforward. So here we have a question. So here we have a very quick question by this Doolittle method. That is, we have given a system that is 2x plus y minus z equals to 8, 4x plus 5y minus 3z equals to 9, minus 2x plus 5y minus 2z equals to minus 5. Now just write it in the matrix form, that is ax equals to b, where this a equals to 2, 1, minus 1, 4, 5, minus 3, and this minus 2, 5, and minus 2. And taking this b as 8, 9, and minus 5. Now assuming this a is equals to LU, and both this L and U are basically lower and upper triangular matrices. So from A is equals to LU, we obtain this U11 as 2, U12 as 1, and U13 as minus 1. Now writing these into the matrix form, and on comparison, we get this L21 U11 equals to 4. Therefore, this 2L21 equals to 4 and L21 equals to 2. Similarly, L31 into U11 becomes minus 2. This twice of L31 equals to minus 2. And this L31 becomes minus 1. Again, comparing the second row of U, we get this L21 U12 plus U22 equals to 5. Then substituting this 2 into 1 plus U22 equals to 5. So U22 becomes 3. Next is L21 into U13 plus U23 equals to minus 3. Substituting this 2 into minus 1 plus U23 equals to minus 3, and we get this U23 equals to minus 1. Now comparing the second column of L, we get this L31 U12 plus L32 U22 equals to 5. And on substituting, minus 1 into 1 plus 3 times L32 equals to 5. This 3L2 equals to 6 and this L32 becomes 2. Now finally we get this L31 into U13 plus L32 into U23 plus U33 equals to minus 2. Then substituting this minus 1 into minus 1 plus 2 into minus 1 plus U33 equals to minus 2. We get this 1 minus 2 plus U33 equals to minus 2 and U33 equals to minus 1. And finally we get this L matrix as 1 0 0 2 1 0 minus 1 2 and 1, and this U matrix as 2 1 minus 1 0 3 minus 1 0 0 minus 1. Now we have successfully factorized the matrix into the product of a lower triangular matrix and an upper triangular matrix. Now the actual solution becomes much easier. So we first solve this Ly equals to B now, taking the multiplication of these two matrices and equate it to this B matrix as 8 9 minus 5. So we get from the very first equation this y1 equals to 8. With the second equation, this 2 into 8 plus y2 equals to 9, and hence this y2 becomes minus 7. And by the third equation, this minus 8 plus 2 into minus 7 plus y3 equals to minus 5. Then minus 22 plus y3 equals to minus 5, and hence this y3 becomes 17. Therefore, this y vector becomes 8 minus 7 and 17. Now using the back substitution method, we have this ux equals to y. Again multiplying these two matrices together and equate it to y matrix. That is this 8 minus 7 and 17. And from the third equation, we immediately get this z equals to minus 17. By second equation, we get this 3y minus z equals to minus 7. And substituting this z equals to minus 17, we get this 3y plus 17 equals to minus 7. 3y equals to minus 24, and hence this y becomes minus 8. And the first equation, 2x plus y minus z equals to 8. On substituting this y equals to minus 8 and z equals to minus 17, we get this 2x minus 8 plus 17 equals to 8. 2x equals to minus 1, and this x becomes minus half. So this becomes the solution. Now we know that our original system is this ax equals to b. Since we have decomposed the coefficient matrix as this a is equals to LU, and we substitute this into the original equation, so this LUX equals to b, or simply this LUX equals to b. Here we have the three matrices together multiply this L into U into X. So instead of multiplying this U and X every time, we introduce a new intermediate variable as Y. This Ux equals to Y, where just Y is just a temporary vector introduced to simplify the computation. Now substituting this Ux by Y, therefore this LUX becomes B. And hence this Ly becomes B. So we have transformed one difficult problem into two much simpler problems. Just need to solve this Ly equals to B using the forward substitution, because L is a lower triangular matrix and this gives us the intermediate vector Y. Now use this value of Y and solve Ux equals to Y using the back substitution, because U is an upper triangular matrix, and finally we obtain the X matrix. So today we started the LU decomposition method, one of the most efficient direct methods for solving the system of linear equations. We began by understanding why LU decomposition was developed and saw that repeatedly applying Gaussian elimination becomes inefficient when solving multiple systems that shares the same coefficient matrix but having the different right hand side vectors. We then learned the concept of matrix factorization, where the coefficient matrix is expressed as a product of a lower triangular matrix and upper triangular matrix. And after deriving the decomposition, we introduced the intermediate vector as y equals to ux, which allowed us to divide the original problem into two simpler systems, this ly equals to b, which we solved using the forward substitution. This ux equals to y, which we solved using the back substitution. And finally, we solved a numerical example and saw how this LU decomposition provides a systematic and computationally efficient approach to solving linear systems. So one important point to remember is that this LU decomposition is especially advantageous when the coefficient matrix remains unchanged but the right hand side vector changes, and in that situations the matrix L and U are computed only once, and hence every new system can be solved quickly using this forward and back substitution. So in the next lecture we'll study the Jacobi iterative method, our first iterative method for solving the system of linear equations. Unlike the direct methods we have studied so far, the Jacobi method starts with an initial approximation and generates the successive approximation that gradually converges to the required solution. So we'll understand the concept of iterative methods, derive the formulas, and discuss the convergence condition and solve a detailed example stepwise. So thank you so much for watching, and if you found this lecture helpful, please like this video and share it with your classmates and subscribe to MathMade Easy to continue learning numerical analysis through detailed theory, complete derivations, and the university level solved examples. Until then, keep learning, keep practicing, and keep questioning. And I'll see you in the next lecture.